Week 11 Hands-on Project, Stock Price Prediction. Welcome! In this lesson, we will tackle time series forecasting using Python. We will work step by step with the airline passengers dataset. By the end, you will know how to process, visualize, and build a simple model to predict future stock or passenger numbers. Ready? Let us dive in. Running the cell now. We prepare our dataset. We ignore warnings to keep output clean. We import pandas for data handling. We use matplotlib for plotting charts. Import numpy as np. We set the random seed to 42 for reproducibility. We download the airline passengers data from the web. We read the dataset, turning the month column into real dates for analysis. We print the size of the dataset. It shows how many rows and columns we have. We preview the first few rows to make sure our data looks correct. We plot airline passengers over time to see overall patterns together. Running the cell now. This output shows that the dataset contains 144 monthly records of airline passengers from 1949 onward, with a single key column, passengers. The initial few rows confirm the time-indexed format needed for time series analysis, and the plotted line chart reveals a clear upward trend with seasonal fluctuations, setting the stage for forecasting passenger counts in this project. Practice: which years appear in the first 5 rows? Check the preview to see. Step 1. What is a time series? A time series is a sequence of data points measured over time. Stock prices, weather reports, and website traffic are all real-world examples. We will learn how to analyze one. Running the cell now. Let us check if we have any missing data points. If there is missing data, we need to handle it to make predictions reliably. Running the cell now. This output shows that there are 0 missing values in the passengers column, meaning our time series data is complete and ready for analysis. Noticing this is important because missing data can affect the accuracy of time series models. This step ensures the integrity of our dataset before we explore trends over time. Filling missing values helps improve prediction quality. We use forward fill to replace missing values with the last known value. Now, let us confirm that there are no missing points left. Running the cell now. Here, the code fills any missing values in the passengers column using forward fill, ensuring no gaps remain in the time series data. The output confirms that there are now 0 missing values, which is crucial for accurate time-based analysis and modeling. This step highlights the importance of having continuous data points in a time series. Step 2. Understanding your data. Let us look at basic statistics. This helps us understand scale, trends, and spot unusual numbers. Always check before modeling. Running the cell now. We print summary statistics to understand minimum, maximum, and average passenger numbers. This overview is helpful to spot outliers or odd values early. Running the cell now. This summary gives us a quick overview of the passengers to data, showing there are 144 entries with an average of about 280 passengers per month. Notice the wide range from 104 up to 622, indicating varying passenger volumes over time, which could reflect seasonal trends or special events. These statistics help us understand the data's scale and variability before deeper analysis. We create a rolling mean, which smooths the data. A moving average uses the last 12 months for each point, showing trends more clearly. We plot both original and smoothed lines to compare. Running the cell now. In this plot, notice how the rolling mean smooths out the month-to-month fluctuations in passenger numbers, revealing the overall upward trend over time. The key insight is how the moving average helps us understand the general pattern without being distracted by short-term variability, which is crucial for interpreting seasonal or noisy data accurately. Step 3. Splitting data for training and testing. To predict the future, we train a model on past data. We then test our prediction accuracy by keeping some data out for checking. Running the cell now. We split our data into two parts. We keep most for training and set aside the last year to test our predictions. This way we can see if our model predicts new values well. We print the size of each set to confirm the split. Running the cell now. Here, we split the dataset into training and testing parts, with the last 12 months reserved for testing. Notice the training set has 132 rows and the test set has 12, both containing 2 columns. This division ensures the model learns from most of the data while we validate it on the most recent year. This step is crucial to mimic real-world forecasting by evaluating predictions on unseen future data. It is helpful to visualize how our data is split. We create a figure. We plot training values in blue. We plot test values in another color so we can see the future period clearly. We add a useful title. We add a legend to show which part is which, then display the chart. Running the cell now. This plot shows how the dataset is divided into training and testing sets, with the training data in blue and testing data in orange. Notice how the training set includes earlier time points, which the model uses to learn patterns, while the test set holds later points to evaluate its predictions. This split is crucial for validating that our model can generalize to unseen data, not just memorize historical trends. This line is a comment explaining that we are using a naive forecasting method where the last observed value is carried forward. We create a copy of the test data frame to store the naive predictions. We assign the last passenger count from the training data to all entries in the naive prediction column. We plot the training data passenger counts over time with a labels train. We plot the test data passenger counts over time in orange with a label test. We plot the naive prediction for the test set in green with dashed lines, labeled a naive prediction. We add a legend to the plot, set the title, and display the plot. Running the cell now. This plot compares actual passenger counts in the training and test sets with a naive forecast that simply repeats the last observed training value for all test points. Notice how the naive prediction is flat, highlighting its simplicity and limitations. This visual helps us understand the baseline accuracy before applying more advanced forecasting methods. Step 4. Building a simple model. Now, let us build a model that uses past data to predict the next value. We will try a linear regression, a simple method that finds the best fit straight line. Running the cell now. To use regression, we turn time into a number for each month. We use NumPy to create an increasing sequence for the training period. Each row gets a time number. We do the same for test data, starting where training left off. Running the cell now. Here we've added a new column called OTime to both the training and test datasets, assigning each data point a sequential number. This step transforms our data into a format suitable for linear regression by providing a clear independent variable that represents the passage of time. Notice how this setup allows the model to learn a trend over time and predict future values accordingly. This comment describes performing a simple linear regression fit. We import linear regression from scikit-learn. We create an instance of the linear regression model. We select the time column from the training set as our input features. We select the passengers column from the training set as our target variable. We train the linear regression model on the training data. We make predictions on the test data using the trained model. Running the cell now. This code fits a linear regression model using the time feature to predict the number of passengers, learning a best fit line from the training data. Although no textual output is shown, the key result is the test_pred array, which contains the model's predicted passenger counts for the test period. This step demonstrates how to build the simplest predictive model that captures the overall trend in the data based on time. Let us compare our regression forecast against real values. We plot training data to provide context. We show test period values. We draw our model's predicted line in red. We add labels and display the plot. Running the cell now. This plot shows the actual passenger counts for the training and test periods alongside the linear regression forecast for the test set. Notice how the red prediction line attempts to follow the trend of the orange test data, though it may miss some seasonal fluctuations. This visualization helps evaluate how well our simple linear model captures the overall pattern in the data. It is important to check how far off our predictions are. Mean absolute error, or MAE, gives the average distance between predicted and real values. We calculate the error for the naive method. We calculate the error for our regression model. We print both errors to compare results. Lower error usually means better predictions. Running the cell now. Here, we compare the prediction errors of the naive method and our linear regression model using mean absolute error, MAE. Notice that the linear regression has a lower MAE, 58.66 versus 76.00, indicating it predicts passenger numbers more accurately. This demonstrates the benefit of building a model to capture trends in past data, improving on simple baseline approaches. Try this. What does a lower MAE score tell us about the model's performance? Step 5. Making a simple forecast for next year. Let us use our regression model to predict the next 12 months. Real data is not available, but we can see the forecast as a dotted line. Running the cell now. We add a comment explaining that we are forecasting the next 12 months. We create the next 12 time points after our dataset. We use the regression model to predict values for those months. New dates are generated for each of the next 12 months. We plot all our original data to provide context. We show our model's 12-month forecast as a red dotted line. We add a legend and title and display the prediction. Running the cell now. This plot shows the original passenger data in a solid line, with the next 12 months forecasted as a red dotted line extending beyond the available data. Notice how the forecast follows the upward trend captured by the regression model, demonstrating how we use the model to predict future values even when real data isn't available. This step highlights how a simple regression enables us to visualize expected trends moving forward. Step 6. Wrap up and next steps. In a real project, you could try more powerful models such as ARIMA or LSTM. You might also add extra features such as holidays or weather. But a simple linear model is a great start and teaches vital concepts. Running the cell now. Here are some best practices as you build forecasting skills. It is vital to plot your series to spot patterns and unexpected changes. Keep test data separate so you get a fair estimate of performance. Try several models and keep checking which works best for your situation. Running the cell now. This output highlights key best practices in time series forecasting, emphasizing the importance of visualizing data to identify trends and seasonality, avoiding overfitting by testing on separate data, and comparing multiple models to find the best fit. These reminders connect directly to the lesson's wrap-up, encouraging learners to build on their foundation by exploring advanced models and incorporating additional features for improved accuracy. Challenge: Mini-project. Try using ARIMA or another package to forecast the same series. Can you improve the MAE over the linear model? Share your plots and findings in the comments. Running the cell now. If you found this project helpful, subscribe and let us know what you'd like to learn next. Lesson recap. We covered time series basics, data cleaning, simple prediction methods, and model evaluation. Now you can apply these steps to predict the future for any sequence of data. Keep learning and exploring. Running the cell now. Thanks for learning with us. Like, subscribe, and hit the bell for more tutorials. See you in the next lesson. Running the cell now.